Hi everyone, so this is section 2.2, and in this section we're going to talk about two other types of limits, both of which involve infinity or that concept of infinity. So the first is about infinite limits and the second is limits at infinity. So let's go ahead and start off by trying to understand what these two types of limits are. Starting off with infinite limits. Infinite limits are limits of functions that are either increasing or decreasing without bound as x approaches a certain value c. So notation-wise, if we were to write that out, that means I'm trying to find the limit of a certain function as x approaches c, but I notice that that function is increasing without bound. So that means I could either say it does not exist, or I could say it goes to positive infinity, or if it's decreasing without bound, I would say it goes to negative infinity. So what type of a function would we have where this might be the solution? Well, let's say that I had the function, so just maybe as an example, let's say that I had the function f of x is equal to 1 over x minus 3. And I wanted to consider two different limits. The first one would be the limit as x approaches 3 with a little positive sign of f of x. And the second is the limit as x approaches 3 with a negative sign of f of x. Well, if I try direct substitution, which is what we learned in the last section, then I would try to substitute the 3 directly into the function. I would end up with 3 minus 3, which is 0. So I get 1 divided by 0. This is not an indeterminate form because it's not 0 divided by 0. So that means I probably cannot simplify the expression, and I can't. There's nothing to factor or cancel or anything. So I can't simplify, and direct substitution isn't answering my question. So what I'll want to do is explore this function either through a graph or through a table. Well, let's take a look at a graph of this function. So we notice it's a rational function, and the denominator would equal 0 when x equals 3. So that is where we would have our asymptote. So the function would actually look something like this. Two nice smooth curves, but a break at x equals 3. So when we go back and we try to evaluate these one-sided limits, we notice this one has a plus sign here. That means we're looking at the function from the right of x equals 3. So we just kind of put our finger on the function here to the right of x equals 3. And as we approach x equals 3, what is the function doing? It's going up here to infinity. So it's increasing without bound. And even though infinity is not a number, it's a concept, we can use it as our answer here because it displays like it displays a description of what's happening with our function, which is that it increases without bound. And then if we check out the second limit, the limit as x approaches 3 with a negative sign, which means from the left of x equals 3, as we get closer and closer to x equals 3 from the left, and we follow the function to see what's happening, we notice that it's going down and it's decreasing without bound. So to demonstrate that answer, we can say that that answer to that limit is negative infinity. So these are infinite limits. And the way that we determine these, and like honestly, like when you look at the original problem, you may not notice right away that it is a limit that involves infinity. The only thing that might give you that indication is that you look at the function and recognize that it's rational, so it might have an asymptote. And then if you look further, you notice that the asymptote is equal to this value right here. So, you know, those kind of things clue you into the fact that you might have a limit at infinity, but infinity is not in the original problem. You have to be savvy enough to recognize what you're doing. So once again, what do we do here? What we do is we try direct substitution, And when we try direct substitution, we recognize we probably have an asymptote because it's 1 divided by 0, which is undefined. So then we either explore the graph or we can create a table. I haven't done any examples with tables because it's a little bit cumbersome. There's some good examples in the book, or if you would like, especially if you have a graphing calculator, there's a way to use the table that's amazing. And so let me know if you'd like to go through that with me in office hours or something. I'd be more than happy to do that. The second concept here that we're looking at is limits at infinity. So when we're trying to consider limits at infinity, what we're really looking at is endpoint behavior. So when we want to consider the endpoint behavior of a function, we find the limit as x approaches negative or positive infinity. So like when you look at our function here, what do I mean by that? As x goes to negative infinity, what is happening to the function? I want to look and see, is it leveling off? Is it going down to negative infinity? What is it doing? This is called the endpoint behavior. So why would this be interesting to us as business students? Well, if I'm considering like the cost function, for example, especially the average cost per unit, and I'm looking at its function, if I want to see what happens to the average cost per unit as production increases, in other words, as x goes to infinity, that is a limit question, and it's a limit as x goes to infinity. It is a limit at infinity. Notation-wise, just really quickly on that, and I didn't really leave space for myself here, but notation-wise, what we're looking at here is the limit as x approaches infinity of a function, or the limit as x approaches negative infinity of a function. And for us, we're normally looking at this one here. The reason why is we're often dealing with this average cost per unit function, and we're trying to study what is the average cost per unit as production increases. So again, as x goes to infinity, the average cost per unit tends towards what? So that we can understand what's going to happen to our costs as we increase production. So because we're talking about rational functions, let's remember kind of a basic algebra fact, but we're going to write it in a calculus way, and that is the limit as x goes to infinity of 1 over x is equal to 0. So let's think about what I'm saying here. We have this limit of 1 over x, and x is going to infinity. So infinity, again, is a concept. It's not a number, but it's just saying that x is getting larger and larger and larger. So if we have a fraction, 1 divided by some value, if x is getting larger and larger and larger, that means the denominator of this fraction is getting larger and larger. So we're taking this 1 and we're dividing it by a larger and larger number, which means that the overall value is going to get smaller and smaller. And sorry to really dig into this more, but I feel like you need to understand this concept. This might be kind of silly, so sorry, but if you have 1 pie and you have to divide it by 2 people, you're going to get a big piece. But if you have that 1 pie and you have to divide it by 20 people or 100 people, I mean, the more people you have to divide that pie into, you're going to get a smaller and smaller amount. If you have to divide it by an infinite number of people, which of course is impossible because infinite is not a number, but if you had to, think about the concept, the amount of pie you're going to get is going to be so small, you might as well just round it off to 0. So we use this concept to help ourselves to consider these types of limits in a more algebraic way. So let me show you how to actually do that. Also, just maybe a little side note here. These problems are different from the previous problems. Remember, with infinite limits, we don't even know that our problem involves infinity until we start working through the problem. But in these types of problems, we know that it involves infinity because it's the limit as x approaches infinity. So when we have that situation, we want to use this process that I'm going to speak of right now. One last little thing I want to throw in before we get into some examples, and that is this idea of horizontal asymptotes. So horizontal asymptotes, let's look at our example from above that 1 over x minus 3. So my function looks like this. And let's say that I was trying to find the limit as x approaches positive infinity of this function f of x. So let's consider that. So this is definitely one of these situations where x is going to infinity, and basically what it's asking us for is the endpoint behavior of this function. So in other words, what's happening at the end of this function all the way to the right of this function? Is it increasing without bound? Is it leveling off? What is happening here? Well, when we look at this function, we notice that it's kind of leveling off. As a matter of fact, this function is going to get closer and closer and closer and closer to 0. So if we were to evaluate this limit as x goes to infinity, we would actually just round it off by saying that the answer is 0, because it's getting so close to 0, again, that it's approximately equal to 0. A little side note on that, if we were to ask for the limit as x approaches negative infinity, we also would get 0, because as x is getting smaller and smaller and smaller, so as we go further and further to the endpoint behavior to the left, because it's negative infinity here, we notice it's also leveling off and it's getting really, really close to 0. Even though it's always going to be a little bit below 0, it's going to get so close to 0 that we just kind of round it off and say the answer is 0. So this kind of brings into play these two comments just real quickly, and then we'll get into some examples of endpoint behavior and also horizontal asymptotes. So endpoint behavior is just telling us that when we do a limit as x approaches infinity, we're looking for the endpoint behavior. That's what we're doing. Horizontal asymptotes, we have a horizontal asymptote whenever we have a curve that kind of levels off like this. So if we have a curve that levels off like this, we say there is a horizontal asymptote. And in fact, in this particular instance, the horizontal asymptote is at y equals 0. So for this particular example, we would say it has a horizontal asymptote of y equals 0. We're not going to spend a whole lot of time on that, nor am I going to ask you questions like that on your homework. I just feel like it was important to get that concept out there. Okay, let's finish this video off with some examples. Okay, so to start, let's look at a couple of examples that end up being limits at infinity. So number 1, say that we have a function f of x is equal to x squared plus x minus 2 divided by x minus 1. And we want to try to evaluate the limit as x approaches 1 from the left, and then the limit as x approaches 1 from the right, and then we'll look at the limit as x approaches 1 of this function. Well, you hopefully are in the habit now of noticing this is a rational function, and so we might decide to try to simplify. And if we do that, we would get x plus 2 times x minus 1 divided by x minus 1. So these values are going to cancel out. So this function can actually be simplified into the function x plus 2. So when we try to evaluate that function, we notice that it is a nice function, and therefore I don't have to worry about whether it's from the left or from the right. I can just use direct substitution, substitute 1 in place of this x value, and I get 1 plus 2, which is 3. And then also on this one, because it doesn't matter if it's from the left or from the right, if it's a nice function, I can just use direct substitution. And now, because the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right, the answer is 3. Okay, so I kind of tricked you on that one because you thought I was going to do a limit at infinity, but it wasn't. But I just want to show you, like, that's what it looks like. You just want to jump into the problem, try what you know, and then if things start blowing up, you have to now take into consideration that it might be an asymptote. Let's take a look at a second example. So this one, we're going to have a function, I'm going to call it g of x, and it equals x squared divided by x minus 5. And we're going to evaluate the limit, you probably guessed it, as x approaches 5 from the right And then from the left, and I'm running out of room here, but we'll just kind of squeeze this in, the limit as x approaches 5. Okay, so you can see that this function, again, it's rational, so you try to simplify it right away, and you notice, oh, I can't simplify it. I can't factor this, and it's not going to cancel out with x minus 5. Therefore, maybe I need to consider a graph, because if I try direct substitution, I'm going to get 0 in the denominator. So let's go ahead and take a look at the graph of this function. Now, just as a reminder, you can draw the graphs using Desmos if you would like, or you can use a graphing calculator. It's a good practice just to know some of these more common graphs, but it's not a requirement for our class. So please reach out if there's anything I can do to help you with the graphing aspect of these types of problems. Okay, so if we were to graph this on a graphing calculator or in Desmos, we would get something that kind of looks like this. And so when we look at this function, we notice right away that it's broken at x equals 5, because like we said, if we substitute in x equals 5, we'll get 0 in the denominator. That gives us an asymptote in this denominator. So when we evaluate the limits, we just need to look at the picture. This says the limit as x approaches 5 from the right. So we look at where x is equal to 5 from the right. So coming from this direction, let me actually help out a little bit here. So from this direction, I look at the behavior of the function, and I notice that it's going up to positive infinity. That means that the limit as x approaches 5 from the right is positive infinity. Another way that we can say that, of course, is that it increases without bound. All right, let's go ahead and take a look at the next limit. So this limit is asking me for the limit as x approaches 5 from the left. So I look to the left of x equals 5, so approaching as we come up to 5 from the left, and I look at the behavior of the function, it's going down to negative infinity. And so that limit, again, is asking me for the behavior of the function, and so I will say it's going to negative infinity. Also, I could say it decreases without bound. And then for the very last piece, remember when we're looking for this limit, again, I've said it a couple times here, but if the limit from the right is not equal to the limit from the left, then the limit as x approaches that value does not exist. So remember, up here, the limit from the left was equal to 3. The limit from the right was equal to 3. Since they're the same, that means if I were to draw a picture of this function, it would be coming together at x equals 1. It would be coming to y equals 3, excuse me. And so that's why the limit is equal to 3. But this one we can even see in the graph. It's broken. Therefore, the limit does not exist, and that is our final answer here. Okay, so that is it for this video. There's one more topic that I want to introduce for this section, but it has its own little video because it is a special consideration. So keep up the great work, everyone.